All right. Hello, everybody, and welcome to the DSM Advanced Materials Forum. And also, as you can see, welcome to my home. Because of the current coronavirus situation, we decided in the interest of the health and safety of everybody to, rather than having everybody travel, to record everything from our home offices. I can imagine that may also be where you're going to be watching this from. But in case you have any questions, please use the chat functionality to ask anytime during the presentation, and we'll try to get back to you with answers as soon as we can. So my name is Michael Valet. I'm a material scientist at DSM. I have a background in polymer physics, and what I'd like to talk to you about today is what the transition towards more connected and sustainable mobility is going to mean for materials, particularly in the area of electromagnetic shielding. And it maybe seems a little bit funny to be talking about mobility at a time now when suddenly people are restricted in their mobility, but at some point, transformation is going to resume, and in fact, it's already underway, because it's not just far future self-driving cars that we're talking about. More connected mobility is actually happening already. Um, just examples you can read about in the news. Maybe you have them in your own vehicle, where, for example, car-to-X networking is allowing vehicles to interact with traffic systems in major cities, traffic light systems, to help drivers detect dangerous systems, optimize traffic flow so you know exactly what speed to approach a red light or a green light, helping people find parking places so they're spending less time and fuel driving around looking for somewhere to park. So already this is beginning to happen, but it's really just the very beginning of what's going to be a huge disruptive transformation, not just for the automotive industry, but actually for a whole relationship potentially with our vehicles. The 5G transformation is going to mean that suddenly there's going to be much more pervasive, high speed wireless communication. All kinds of devices are going to be talking with each other. Increases in sophisticated self driving technology are going to make vehicles more and more autonomous, which is going to rely, of course, on all these signals they're exchanging with their environment, with the traffic infrastructure, with other cars. Um, Suddenly drivers are going to be doing different things in their vehicles than paying attention to driving around. Maybe you're interacting with your entertainment system, talking with others in the car, calling home, whatever it is. So a lot of things are going to be changing. And of course, there's a whole lot of discussion, different opinions about how fast this is going to be, when it's all going to happen. And really one of the concerns about which people, driving this disagreement is related to safety. When it comes to automation, autonomous driving, how reliable is it going to be to trust that our cars are going to be able to drive themselves and are going to be safe both for the people inside the vehicle and for everybody else around them? And that's essentially coming down to the reliability of all these electronic systems and wireless communications that are going to be managing this autonomous driving. So suddenly we're going to be going from, if you think about a historical environment where the important radiation coming to your car was just the radio that you're going to be listening to. Now your vehicle is going to be bathed in all kinds of external signals, essentially. Some of which are very important to receive, and others which are going to be noise. Some are going to be coming from other vehicles, from the traffic infrastructure again, from all kinds of other communications, from underneath the road. But you also have signals that are coming even from within your vehicle. Whether, if you think about the electronic motors that are going to be in new vehicles, whether they're driven by batteries or hydrogen, you're still going to have an e-motor, um, and that's generating all kinds of electromagnetic fields. And then, of course, all these electronics within your vehicles are going to be generating their own signals. And somehow you need to find a way that all these crucial electronics are all going to be able to function, to receive the signals that they need to receive, and not receive any interference from all this other communication and electromagnetic phenomena that's going to be surrounding them. And that's where we come to the topic of electromagnetic shielding. Basically, we need to find a way to actually protect all these sensitive electronics from the radiation which is going to be around, so that all of these systems can operate in a safe and reliable manner, and so this transition can actually happen. And this is where material science and physics actually comes in. How does electromagnetic shielding work? Um, And what I'm going to do today is take you through a bit of material science perspective, a bit of a dive into what is the physics underlying it and what does it mean for materials design, for material selection, especially when you're thinking about lightweight alternatives to designing with metals. And yeah, so maybe to just go into the basics of EMI shielding, I have illustrated here really kind of the simplest, most generic configuration you can think about for a shielding situation. You've got a source generating some kind of electromagnetic radiation, could be a range of different frequencies, and that radiation travels through space, electromagnetic wave, and reaches your shield. And if a shield is going to shield that radiation, it has to do one of two things. It can reflect, it can bounce that radiation off, or it can absorb the radiation. And whatever isn't either reflected or absorbed is transmitted through to the other side of the shield and reaches the receiver that actually is what you're trying to protect with that shield. And when quantifying the performance of a shield, normally you talk about the shielding effectiveness. This is something, typically, this is given in units of decibels. So it's a logarithmic scale, and it's essentially the ratio in a logarithmic scale of the shield the field strength which is coming in to the field strength which is coming out. And it turns out that electrically conductive materials, like metals, for example, are actually both very strong reflectors and also extremely strong absorbers. And that's why these are conductive materials are often used for shielding. So actually, why is that? What makes a conductive material such a good shield? Actually, it gets down to the definition of a conductor, which is that electrons in a conductive material are able to move freely. So if we now think about what's actually going on, imagine again you've got an incoming electromagnetic wave traveling through space towards a dipole planar shield. Now, if you think back to your electromagnetics class, whenever that might have last been, that electromagnetic wave, it consists of oscillating electric and magnetic fields perpendicular to its direction of motion. So you've got an E field moving up and down like this, approaching your planar shield. Now, when it reaches the shield, electrons in the shield feel that incoming oscillation in the electric field, and they begin to move in response. And they're able to because the shield is conductive. And if you also think back to that old physics class, when you have an electron that's accelerating, that's beginning to move, that actually generates its own electromagnetic wave. That is the reflection. So the wave comes in, stimulates motion of electrons. That stimulated motion generates reflection. And the more conductive your material is, the more able your electrons are to move and the more reflection you get. Also, as those electrons are moving up and down in your shield, they're also dissipating energy, and that leads to attenuation of the wave. So that's actually the absorption effect. And so high conductivity, more ability for your electrons to move, results both in more reflection and more absorption. Now, let's go back to those decibels, talking about what they actually mean in terms of the fields that are coming through. The power of an electromagnet transmitted by an electromagnetic wave is actually proportional to the square of the field. So um, actually, it means a pretty simple relation when it comes to thinking about between the decibels of shielding effectiveness and the power transmitted relative to what's incoming. Every 10 decibels gives you a factor 10 multiplicative reduction, logarithmic scale, remember, of the power which comes through. So 10 decibels means only 10% comes through. 30 decibels means I've reduced my power by a factor of 1,000. 50 decibels, 100,000. 70 decibels, 10 million. Cool. Okay, pretty simple. But then how much shielding do we actually need? How many decibels is the right number? And of course, that's really going to depend on your application, how sensitive the electronics are, how safety critical it is, all kinds of things, how you've designed your system, how much redundancy. When you look, these are examples for a lot of different devices of the kind of shielding requirements that we've seen cited. It'll and often what you see coming back um, is that really people are interested in shielding levels of at least 40 to 60 decibels in a lot of these types of radio frequency applications. And actually, when you think about those numbers I was just mentioning, this is really a lot of shielding. We're talking about a factor of 10,000 up to maybe a factor of 1,000,000 times reduction in the power coming. This really begs some questions, drives conversations. How much shielding really is necessary? Is a factor million actually what is needed for a particular application? And so that question mark is also going to, of course, be balanced by the safety criticality of a lot of these components in in an autonomous vehicle. When somebody's life is on the line, then you obviously want to have a lot more safety margin than if it's just a matter of having a little bit of distortion on your cellular phone. So, um, yeah, this is one of the this question of how much shielding is really needed. I expect to be something that will be debated and evolving as more and more attention goes into this subject in the future. Now, whatever the level is, you have a challenge, of course, in finding a material in an enclosure design which is actually going to give you that level of performance you're looking for. And that's especially true if you're looking for lightweight alternatives to a piece of metal. So, really, the challenge from a materials view, conductive materials like metals are fantastic for shielding. That's known. They're a well-established reference solution. People know a lot about what they can do with them. But just as has been known for in a lot of other areas, plastics actually offer a lot of design advantages when it comes to both cost down, but also for lightweighting. So there's a lot of attention on, okay, can we um, replace, do we have to use metal to get this shielding, or can we find plastic-based solutions that give us other advantages and still give us the reliable shielding performance that we need? The problem is plastics are insulators. In other words, electromagnetically transparent. So how are we going to make them shield? Now there are conductive plastics available, but what it boils down to, there's there's sort of a not too huge set of some basic shielding options which are available today. So one is to stick with metal enclosures. This gives you high shielding performance. Not necessarily going to be the lightest weight solution. Total cost of production, maybe some question marks there too. But if you're looking for the highest level of shielding performance, then stick for the time being with metal. Turns out metals are actually such good shields that you can even use them as a very thin coating layer on top of non-conductive, normal insulating plastic, and also get pretty good shielding. But that's where some of the reliability questions come in. How well adhered is that coating layer? Is it going to last through the life of the part? What happens if I get a scratch? Does that affect my shielding performance? So yeah, some of the considerations come up with those kind of solutions. You can also look towards conductive plastics, not only for intrinsically conductive polymers, but also just by adding conductive filler, you can make plastic materials electrically conductive. And is that going to be enough to shield? Um, Even more extreme, you can go not towards moldable composites, but instead moldable compounds, but instead towards continuous fiber carbon fiber composites, whether in a thermoset or a thermoplast kind of matrix, and that allows you to actually achieve really high conductivities together with pretty exceptional mechanical properties. So these are some of the kind of options that are available if you're thinking about metal replacement for shielding. So um, now to take a little bit of a look at, well, okay, I'm considering a conductive plastic or a composite. Is it actually going to be good enough for the shielding needs of my application? And to think about that, it boils down to, okay, how conductive are they? So here I show the electrical conductivity of some example materials. The units of electrical conductivity volumetrically in a material are the units of Siemens per meter. That's the inverse of ohms meters or ohm centimeters. The resistivity, which you may also be familiar with. You can work with either one. But here I'll use conductivities just to give you a sense of the scales involved. A typical metal, so like silver or aluminum, has an electrical conductivity of more than 10 to the seventh Siemens per meter. If you look at a standard non-conductive polymer matrix, then you're kind of in the range of 10 to the minus 13th, 10 to the minus 10, something like that, Siemens per meter. So we're talking about a gap in conductivity of 20 orders of magnitude between an insulating plastic and a conductive metal. It's pretty big. And that's where conductive plastics come in. And So for example, if you take a carbon black, a highly carbon black fill polyamide, then maybe you're getting towards around 10 Siemens per meter. Start working with carbon fiber, then you can get into the hundreds. And with carbon fiber composites, then you can be getting into the region of 10,000s. So these kind of conductive plastic materials are many orders of magnitude higher in conductivity than in a normal insulative plastic. That's why people call them conductive plastics. But you're still orders of magnitude below the conductivity of a metal. So is this actually good enough? And this is actually where you open the textbook again, because the nice thing about electromagnetic waves is they obey Maxwell's equations, so we can describe what they do. And you can actually pull out a pencil and paper and a book, and you can work out if you have an electromagnetic wave approaching that planar shield. It reflects off the surface, enters the shield, part of it bounces back and forth, a certain amount of power comes out the other side, and you can calculate how much of the power of the shield, power of the wave makes it through that shield. And those are the equations that I've got written down here. And you can use those to predict the performance of a planar shield based on the material's properties, like the conductivity and of course, and it's actually been shown already in the literature that these models agree very well with actual experimental measurements on planar shields. So here on the right, I have an example of experimental data that was gathered, measurements of the shielding performance of different conductive plastic based materials. Um, the dots are experimental measurements, and we're plotting here. It's plotting the shielding effectiveness versus the volume resistivity. So that's 1 over the conductivity. Um, and the solid line is the theoretical value, essentially a plot of that equation that's written on the slide. And you can see the agreement is possible with these models to actually describe very well how a material is going to shield. So let's use these formulas and think about what conductivity level we actually need. So what I do here is I calculate for a 2 millimeter thick shield, just as an indicative thickness of a wall that you might be considering, um, what the shielding effectiveness in decibels is going to be as a function of frequency for a few different levels of conductivity. So the green line at the bottom is 1 Siemens per meter. And you can see you basically have no shielding at all. When you get up to 10 Siemens per meter, then you're looking at around 10 decibels. So, okay, in terms of power reduction, it's a factor 10. Actually, naively, maybe that doesn't sound so bad, but next to these kind of 40 dB requirements, that's really not enough. When you get to 100 Siemens per meter, now you're starting to get to the territory where you're talking about real shielding, although still not at a level high enough for comfort in a lot of applications, 30 dB. And then by the time you're at 1,000 Siemens per meter, then you're able to reach 50 dB or higher, and now you're really working with a nice shielding material. You also see that these curves have a typical shape, basically that the shielding goes up towards the high frequency range. And this is actually related to an increase in the importance of absorption effects at those high frequencies. Basically, as your frequency gets higher and higher, your wavelength is getting shorter and shorter. And so for a shield of a particular thickness, that means you have more wavelengths, more oscillations for the wave to move through it, and that means more chance for absorption to happen. So that's the reason for that. But basically, this gives us a bit of an indicative value of what kind of shield conductivity levels we need if we want to have shielding in a conductive plastic-based material. Okay, and how do we actually then make that happen? The classic way to make a particular polymer matrix conductive is to start adding electrically conductive filler, often carbon-based, carbon black, carbon fiber, for example. And when you start doing this, there's the classic phenomena in this field is what's called percolation. So if you think about adding just a tiny amount of conductive filler, then you're in this situation on the left of this plot here. Then you have isolated particles, which themselves are conductive. But if you try to run a signal through your whole sample, then there's no conductive path for it to make it through. It's dominated by the matrix. So your conductivity stays very low. If you start adding more and more filler, at a certain point, you add enough that you're able to form a conducting path through your entire sample. And at that point, your bulk volume conductivity increases by many, many, many orders of magnitude, even though you only add a tiny bit of extra filler. And the sort of classical problem in the design of conductive composites is all about this percolation threshold. If you read papers, if you read literature on this topic, it always comes up, and it's really all about how do we achieve this percolation threshold, where I move from being an isolating material, electrically transparent, to a conductive material with as little or as cheap filler as possible. But electromagnetic shielding, because of the high conductivity that's required, is actually a pretty different challenge. It's not just do I percolate, it's if I percolate, because that's for sure going to be necessary, do I have high enough conductivity to reach the level that's needed for sufficient shielding? And this is actually where a lot of standard conductive fillers that you might be thinking about using for, let's say, electrostatic dissipative applications actually run into their limits. So here's an example of experimental data from the literature. PA66 combined with Ketchum black, carbon black, one of the most exceptionally high conductivity carbon blacks that there is. And you can see here in this experimental data the classic shape of that percolation curve I showed on the previous plot. You start with an isolating material, you add more and more carbon black. At a certain load, you increase over orders of magnitude in conductivity, and then you reach a plateau. And that plateau is around 10 Siemens per meter. And so that's really still at the point where you don't have a material that's suitable for EMI shielding, even with very low requirements. And this is a point that is sometimes neglected. Um, there's a proliferation right now of research, not only academic research, but also commercial development of all kinds of new examples of what I would call nanocarbons. There's this explosion in availability and variety of nanotubes, nanostructures, graphenes, all kinds of graphite. So this real remarkable collection of new materials which are becoming available. And a lot of the evaluations of how well they work are really focused on this issue of when do they achieve percolation. And often people talk about, hey, can we use these for shielding? But you don't want to check your percolation threshold. The real question is, do they add something when it comes to your peak conductivity? Because that's what shielding requires. One thing that can work to get you there is using metal-based fillers, whether it's stainless steel, fibers, flakes, other kinds of metal particles are able to, by virtue of their very high conductivity, bring the conductivity of your plastic compound up to a high level. But if you're looking for the lightest weight solution possible, these are always going to struggle compared to a carbon-based solution. Okay, so maybe so far it sounds like I'm painting an extremely grim picture, everything being difficult and hard, and oh my gosh, we need so much conductivity. But actually, there's one thing that does really help us out when it comes to using conductive fibers like carbon fibers in conductive plastics, and that has to do with the intrinsic anisotropy of these fiber-based materials. If you remember when I was saying earlier the physics of this reflection and absorption that comes from the conductivity of a material, you have a wave that's coming in, for example, um, normal to your surface. The fields are moving like this, and the electrons are also moving in the plane direction of your shield in this kind of situation. And what that means, it's actually the in-plane conductivity which is determining the shielding performance of that shield, both for the reflection and also for the absorption component. And when you have fiber-based materials, then the alignment of those fibers, either due to the flow fields during injection molding, for example, or if you made a continuous fiber carbon composite and you really align those fibers really directly yourself, um, typically these materials actually have much higher conductivity in the plane than normal to the plane. And so shielding actually, for shielding, that's actually really great. And this higher in-plane conductivity can help with these kind of materials and giving a boost in performance. To replace metals, sticks, often at the through plane conductivity for heat transmission, which is limiting for metal replacement. But here for EMI shielding, we have the opposite situation. Okay, so that was a lot of maybe kind of theoretical sounding background. Now let's take a look at what happens if you actually want to measure shielding performance. Now, this is kind of a typical example of a materials-oriented characterization test, ASTM 4935 standard. It measures in a range of 30 megahertz to 1.5 gigahertz. That's not the only frequency range that matters, but it's a relevant span of frequencies. And essentially what you do is you take a planar sheet of that material and you insert it into a transmission line. And basically you send a plane wave at it and you measure how much of that plane wave comes out the other side and how much is reflected or absorbed. And you compare that to a reference sample where you've basically removed the part of material inside that transmission line. And so this is a nice way to basically, in a standard fashion, characterize how different kinds of planar shielding materials perform. And here's just an example of data from this kind of test we measured together with the Institute for High Frequency Technology at RWTH in Aachen. Um, and these are just examples of the kind of conductivity that is possible to reach with conductive carbon fiber uh, containing compounds. And these example materials here, you see we reach the levels of over 40 dB that we believe are important for EMI shielding in a lot of applications where, let's say, moderate EMI shielding is required, not the highest level, but okay, you're able to get a good level of signal reduction, factor 10,000. These materials, this particular combination we use, we're also able to reach thermal conductivities where in the range of 1 to 2 watts per meter Kelvin through plane. That's also really useful if the electronic device that you're shielding is also on its own generating a lot of heat. Um, One thing you'll notice, these plots here we have, these include both PA6 Aculon-based polymer matrix as well as Zytron PPS. Actually, the shielding performance is really dominated, especially in these high conductivity regimes, more by the conductive filler that you're using than by the polymer matrix that you're selecting. So that gives you flexibility with the polymer matrix to optimize it for other properties. So for example, an advantage of the Zytron PPS is that it's an intrinsically flame retardant material. So you can reach UL94V0 without having to add additional flame retardants. So this is an example of what kind of performance is possible using electrically conductive composites, compounds for shielding. Um, okay, what if that's not enough? What if you need that 60 dB? That's where you can start looking, if lightweight is important, at continuous fiber carbon composites. Because this is where you get into the territory of real high performance shielding materials. As was mentioned on one of the earlier slides, the fact that when you have really long continuous carbon fibers allows you to reach much higher values of this in-plane conductivity. Now you can get to levels of around 10,000 Siemens per meter. And that's really bringing you into the territory where you can really have um, shielding performance that's competitive with metals. And you do also, when it comes to these anisotropy effects, now you need to think at least a little bit about them, not only in versus through plane, but also which direction in the plane. If you only have a purely unidirectional carbon fiber, um, then you're going to have conductivity that's higher in some direction than others. So it's good with these kind of materials if you're shielding that you'd be assembling them, for example, into configuration like a 090 composite stack. Then you have nice uniform shielding performance in all directions. And again, just examples of material performance um, of this kind of material category. These are, in this plot here, I show example data for continuous fiber thermoplastic composites, either a 2-layer 090 stack that's 0.5 millimeter thick, or 4-layer 090 stack, 1 millimeter thick. And you see that with this kind of material, you can get into the range of 60 dB, 70 into shielding performance that's really much more in the territory of bona fide metal replacement. And that comes along with exceptional mechanical properties in these kind of materials as well. So when you're looking for metal replacement where shielding is important, where mechanics are important, maybe it's a structural part, and you're really looking for the highest performance solution, then this might be where I would start. But you do have to take in mind the additional complexities that come with shaping these kind of continuous fiber composites relative to, for example, an injection moldable compound. Okay, so I've been talking a lot about materials, but of course, at the end of the day, it's actually not a material which is going to be doing the shielding. It's going to be an enclosure, which is going to be have its own design considerations associated with it. And the real final performance in your application is going to be governed by this combination of the materials you select with the design of your enclosure. And what's nice here, so again, electromagnetic waves obey Maxwell's equations. And even though for a real enclosure with a complicated shape, you can't solve that with pencil and paper anymore, what you can do is computer-aided engineering simulations. And we find these can be a really valuable tool to try to bridge the gap between materials, design, and ultimate performance. So here's just an example of the kind of simulations that you can do and the kind of things that you can learn. Here you take, on the example here on the left, just a simple rectangular box made up of 1 millimeter thick carbon fiber composite. And then you apply a plane wave on that, and you can basically measure how much of that plane wave gets into the box. Are there some hot spots within the box, for example? And then you can do things like, hey, let's say I can't actually, in practice, have the carbon fiber composite on all sides. Let's say I want to replace the top of the box with a 3 millimeter layer of conductive plastic. Then I can look, and I show this on the plot at the right, for example, at what the impact then is for the shielding performance of the full enclosure. Um, or you can transparent panel, maybe not, it's not too good. Um, So these kind of CAE tools can be a really valuable way to basically do these kind of explorations on the computer instead of having to build a whole enclosure and go to an EMI test facility to find out. And you know, there's actually quite a lot of phenomena that come in that are not present when you're just worrying about a simple planar shield. You're designing some kind of box. Uh, what about gaps that might need to be there? If I have cables that are coming in, or I have some other kinds of features which are going to require holes in my construction, what is the impact going to be on the shielding behavior? Am I going to have resonant modes existing at certain physical locations or corresponding to certain radiation frequencies? What about the radiation source? How far away is it from my box? In the near field, all kinds of different things can happen that you may not see in a standard planar configuration. And so with simulation tools, you can explore a lot of these phenomena and make a much better informed decision, basically, about how to proceed combining materials and design to realize the best performing solution. And so on that note, I'd like to wrap up a bit. When it comes to lightweight shielding design, how do you achieve this kind of electromagnetic shielding that we know is going to be a prerequisite for reliable, safe, connected next generation mobility solutions? Um, how do you get that in lightweight and fuel efficient materials? Ultimately, that's going to be a combination of materials properties with a lot of thinking about electromagnetic physics and engineering, and also some CAE design. Bringing that all together lets you help engineer a shielding solution which delivers on its performance and its reliability while still reducing weight and doing so at acceptable overall cost. And I don't want to claim that this is going to be easy. I don't think it always will, but it will be possible. And at DSM, we really believe that, and we hope to have the opportunity to talk with you about the kind of challenges you're facing in this area and see if we can find some cool solutions together. So once again, please use the chat functionality. We're happy to answer your questions, and hope you've enjoyed this and that you enjoyed the rest of the AMF forum. Please stay safe and healthy in this challenging time. Thanks a lot.